Hello friends, this is Hasiba. Welcome to our next topic on module 3, which is clipping, right? So far in module 3 we have discussed about different types of transformation, that is translation, rotation, scaling, reflection and shear transformation, right? So the first topic under module 3 is about clipping, right? So what do we mean by clipping? Clipping is nothing but selecting a part of the picture which we want to see or which we want to display on any display screen, right? So the definition goes like this: the technique for not showing the part of the picture which one is not interested, right? Or not showing the part of the picture which one is not interested and focusing only on that particular part which people are interested in, we call it as clipping, right? So a graphics package, it allows a user to specify which part of a defined picture is to be displayed and where that particular part is to be displayed on the display device, right? That means that whatever picture we want to, whichever part of the picture we want to see, right? So we can clip that particular part of the picture, and wherever we want to display on the display device, we can do so by making use of a different OpenGL functions. So the next topic is coordinate system. There are basically two types of coordinate system: world coordinates and device coordinates, right? So world coordinates is nothing but a Cartesian coordinate system in which we describe the coordinates of the picture to be displayed, right? So in the world coordinates, the picture will be present, and in the world coordinate system, we describe the coordinates of that particular picture which has to be displayed, right? So the device coordinate system tells us about the coordinates corresponding to the device in which we want to display. That means from the world coordinate system, we will select that particular part of the picture, or we will clip the picture and we will be displaying on the device, right? On the device coordinates, right? So these are the two types of coordinate systems what we have: world coordinate system and device coordinate system. So next topic is viewing transformation system. So what do we mean by viewing transformation? The process of mapping a part of the world coordinate scene to device coordinate system is known as viewing transformation. That means I will be selecting a part of the picture from the world coordinate. World coordinate is nothing but the real picture, right? So that particular part of the picture from reality or from world coordinates, I'll select and I will try to display that particular picture on my device coordinate system. Device coordinate is nothing but my display screen, right? So the process of mapping world coordinates to device coordinates, we call it as the viewing transformation, right? So a world coordinate area which is selected for display, we call it as a window, right? And an area on the display device to which a window is mapped. That means from that particular window, I will map it to a point. This particular point, we call it as the viewport, right? So we say that in short, window defines what to be viewed and viewport defines where it is to be displayed, right? So if in the window, we'll be selecting the picture, what picture I want to display on my display screen, and from in the viewport, I'll be telling where on the screen, right? So which part of the screen that particular picture has to be displayed, right? So window defines what to be displayed and viewport defines where it has to be displayed, right? So this is with respect to viewing transformation system, right? So as you can see here, this is an object in the world coordinates, right? So this is a real world object. Now I am going to clip this particular part of the object, right? So this window, I call it as the clipping window. This is my clipping window, right? So what I'm part of the object I'm clipping this particular part of my cube, right? So this particular part is clipped, right? So you can see here this line and this line, right? So this part of the picture is clipped and it is mapped to my device coordinate system, right? So this is how, this is my display screen and this is how the object in the device coordinate system looks like, right? So this is what we mean by viewing transformation, right? Transforming the coordinates from a window coordinate, transforming window coordinates to viewport coordinates, right? So this is my viewport, whereas this is called as the clipping window, right? So here in case of clipping, we have two cases, right? So the first case is, say for example, we change the position of the window keeping the viewport location constant, right? So what do we mean by that is changing the position of the window. Changing the position of the window means, say for example, now here I have selected this part of the picture, right? So I'll be able to see this part of the picture here on my device coordinates, right? So if at all say I want to display some other part of the picture, say for example I want to display this side, right? So if I want to display this side, then I will be changing my window, right? So window will change, right? And I'll be able to see another part of the object in the same place, right, of the viewport. That is the first case. Changing the position of the window, keeping the viewport location constant, then what I can see? I can see different part of the object which is displayed at the same position on the display device, right? So different parts of the object can be seen which are displayed at the same position of the display device. The second case is, right, if we change the location of the viewport, right? So what do we mean by location of the viewport? Say for example this is my display screen, right? So here I am keeping my viewport. Say for example I want to change the location of my viewport from here to here, right? But the the part of the object which I have clipped, but the part of the object which I have clipped, right, remains the same. This is the part of the object which I have clipped, right? So this same part of the object I am displaying here. I can display here, or I can display here, or I can display here. That means I can display it on any part of the screen, right? So that is my second case. Say for example, if we change the location of the viewport, but I'm keeping the window constant, then the same part of the object is drawn at different places, right? So these are the two types of viewings what I can do, right? So I can change the window, right, keeping the viewport constant, or else I can keep the window constant and change the viewport. If at all I change the window, what I can see is I can see different parts of the object in the same position on my device coordinates. If I keep the window constant, right, then what I can do is I can see the same picture which is displayed at different places on my device coordinates, right? So this is with respect to clipping, right? So changing the size of the viewport means what? We can change the size and the proportion of display objects. That means we are actually having a zoom in and zoom out effects here by making use of these two cases. So the next topic what we have is normalization, right? So what do you mean by normalizing, right? So normalizing means converting, so in between this window coordinates to device coordinates, right? So I can map this window coordinates to normalized coordinates, right? So what are these normalized coordinates is whatever picture you are selecting, you are normalizing it into the coordinate values between 0 and 1. That means this 0 comma 0 is my origin, this is my +1 unit, and this is my -1 unit, right? So if at all I select any point here, this is negative x-axis and negative y-axis, so the point will be -1 comma -1. If at all I select any point in this particular part, right? So since it is positive x and negative y, I will get it as +1 and -1. If at all I select any point here, which is in positive x and positive y, I will get +1 and +1. If at all I select any point here, which is in negative x and positive y, I will get it as -1 and +1, right? So like that, like this at different quadrants, I can select different points, right? So and I will draw this, I will connect these points, right, so that I will get my normalized window, right? So this is my normalization, right? So normalization and window to viewport transformation, they can be combined into a single operation, right? So what we do in this case is the viewport coordinates will range from 0 to 1, right? So if at all I want to convert an object from my window coordinate to normalized coordinate, then my viewport will be between 0 and 1, right? So we say that it is a unit square which is mapped to the output display device, right? So since I have -1 and +1, right? So this normalized window, we call it as a unit square, right? So unit square which is mapped onto the output display device. So in order to do this transformation, right, there are basically, that means in order to do the normalization and window to viewport transformation, right, so we have two methods of transformation. The first method of transformation is called as mapping clipping window to normalized viewport. That means converting a window to viewport. That is the first method of transformation. Second method of transformation is mapping the window to a normalized square, right? I repeat, the first type of transformation is mapping the clipping window to the viewport, right? So I'm mapping window to viewport. This is my first type of transformation. Second type of transformation means window to a normalized square, right? So we'll be discussing these two type of transformations one by one, right? So let us start from the first one, which is converting window to viewport, right? So mapping clipping window to viewport, right? So consider our clipping window, right? So if I take any clipping window, it has 2 points, right? So and on the x-axis and on the y-axis, right? So we say it has the point, right? So which is xw min and xw max, right? And we have yw min and yw max, right? This is the how the clipping window is defined. So if I consider any point in the clipping window, this particular point has to be transformed to the to a point in the viewport, right, at the same relative position, right? So relative position means its position should not change, right? So wherever it was there in the window, the same relative position it should be transformed into the viewport, right? So that is what we mean by window to viewport. So under, if I take my viewport, right, so in my viewport again I have xv min, xv max, right, on the x-axis, right? So yv min, yv max, right? So yv min means what? y-axis value on the window viewport coordinate, right? So yv min and yv max, right? So this particular point, which is xw comma yw on my clipping window, it is transformed to a relative position on the viewport, right? So that it becomes xv comma yv, right? So we say the position xw comma yw in the clipping window is mapped to, it is mapped to xv comma yv in the associated viewport, right? So this is how we'll be mapping window coordinates to viewport coordinates, right? So in order to do this window coordinate to viewport coordinate, right, so we have to do some transformations, right? So in order to do the transformation, what we do here is to transform the world coordinate point into same relative position within the viewport. What we do is we have to consider this particular point, right? So this particular point, how we do is we consider the difference between xv, right? Xv, we consider the difference between xv minus xv min, xv, right? So we have to consider this here, right? The difference between xv and xv min, this length we have to consider, right? So it will be the total xv minus xv min means I will get this particular distance, right? So and the difference between here, which is xv max minus xv min, right? So we have to take the difference between xv minus xv min divided by, right, xv max minus xv min, right? So the same way it's a corresponding window coordinates also we have to take, right? So corresponding window coordinates will be xw minus xw min will be the numerator, and in the denominator we will have xw min minus xw max minus xw min, right? So whatever I write in viewport, same thing I have to write it in window, right? So remember that for the viewport, right, for this particular point, what I do, I will consider xv minus xv min, right? And then I will take the difference between xv max minus xv min, xv max minus xv min. Same thing I have to convert it into xw minus xw min to xw max minus xw min, right? So same thing we have to write it for y coordinates also, right? So we write it as xv becomes yv minus yv min divided by yv max minus yv min, right? And here it becomes yw minus yw min divided by yw max minus yw min, right? So this is how we define the coordinate points, right? So from the world coordinates to the viewport coordinates. Then what we have to do, we have to solve these expression, right? We have to solve this expression so that we will get the value for xv, right? So in order to solve this expression, right, so you have to consider this particular equation here, right? So xv will be equal to what? It will be equal to xv max minus xv min into this entire expression plus xv min, right? So if I multiply this denominator here to the numerator and then add this to xv min, then I will be getting the value for xv, right? So when you do that multiplication, right, so you will get two expressions, right? So this transformation we will get two expression, right? So we call the scaling factors as sx and sy, right? So when we are doing that, when we multiply these two, we will get some values, right? So that values we replace with the two variables, which is sx and tx, right? So why we are taking scaling and translation? Because whenever I'm mapping window to viewport, what it is actually scaling. That means I am reducing the shape of the window, right? So from larger to smaller, right? So reducing the size of the window. Reducing the size of the window is the it means scaling, right? Reducing the size of the window is called as scaling, and the point is moved from this particular point to this point, right? So that means it is translation, right? So mapping of window to viewport is actually scaling and translation, right? So that is why we are taking the along x-axis we'll be taking scaling factors sx and translation factor tx. Along y-axis we'll be taking scaling factors sy and translation factor ty, right? So xv will be equal to sx into xw. What is this sx? This sx, after multiplying this, right? So after multiplying this like this, right, and then solving for xv, we will get the values of sx. Sx will be equal to xv max minus xv min divided by xw max minus xw min, right? So this we got after multiplying this and solving this, and tx we will get one variable xw max xv min minus xw min xv max divided by xw max minus xw min, right? So like this you will get the scaling factors and the translation factors, right? So once you get this, for these variables you have to replace them by tx, right? And this variable you will be replaced with the sx, right? So then finally you will get your xv as xv is equal to sx into xw plus tx, and the same way yv you will get it as sy into yw plus ty, right? So how we got these two? We got these two by just solving these two equations, solving equation number 2, right? What you have to do, xv is equal to take this, multiply with this entire whole thing, right, plus xv min. If you solve this particular equation, you will get two values, right? So one part will be this, the other part will be this part, right? So this entire part you replace it by sx, and this part we have to replace it with tx, right? So that finally we get our viewport equation. Fine, right? So once we get this equation, right, so we generalize it by writing transformation from world coordinate to viewport coordinate consists of the following sequence, right? So what is it? First we have to scale the clipping window to the size of the viewport, right? So we are doing scaling here with the respect to the fixed position, which is our xw min and yw min, right? So what we have to do is we have to consider this particular point, right? So first we will scale it with respect to the point xw min here, right? So we first scale it with respect to the point xw min and yw min, then we go for translation, right? So what is scaling with respect to a fixed point? Scaling with respect to a fixed point actually involves inverse translation, scaling that particular object, and again retranslation, right? So translation, scaling, and retranslation, that is scaling with respect to a fixed point, right? So all these three will be done and it will be scaled with respect to a fixed point. Once it is scaled, then the translation happens, right? So scale the clipping window to the size of the viewport using the fixed position, right? So we are considering the lowermost or the leftmost corner of the window, which is xw min and yw min, the leftmost point, right, as the fixed point. Then afterwards what we do, we translate the xw min yw min to xv min and yv min, right? So once we do that, this is called as converting from window to normalized viewport, right? So this capital M is nothing but your composite transformation matrix, right? So for converting window to normalized viewport coordinates, right? So we write it as, first we will do scaling, then we will do translation. Always we have to write from right to left, right? So first scaling will be applied, then translation will be applied, right? So and our final matrix will be sx 0 tx 0 sy ty and 0 0 1. This is the final composite transformation matrix for converting the coordinates from window to viewport, right? So we just generalize the window to viewport transformation. This is the summary, right? So in window to viewport transformation, what is very important? Relative placement of the object description is very important. That means whichever position you are considering, position of the point you are considering, it should be placed in the viewport relative to its previous position, right? And relative proportion of the object are maintained, right? So how we are maintaining that? By considering the aspect ratio of the viewport is same as that of the clipping window. That means we are considering the scaling factors along x-axis and along y-axis, both are equal. Sx is equal to sy. That is what we are doing here. Whatever value we get for sx, the same thing, just replace x by y. Just replacing x by y, we are calculating our sy, right? So maintaining sx as sy, right? So we'll be able to maintain the aspect ratio of the viewport, right? Otherwise what happens? The world object will be stretched or it will be contracted in either x or y direction when it is displayed on the output device, right? So this we have to keep in mind while converting the window coordinates to viewport coordinates. This is the first type of transformation, window to viewport. So moving to the second type of transformation, the second type of transformation is mapping the clipping window to a normalized square, right? So that means here what we are doing, right? So look at this diagram. We have the clipping window, right? So this clipping window is first transformed, right? It is first mapped to a normalized square. Again, from this normalized square, it will be mapped to the viewport coordinates, right? So in order to do that, we have our clipping window, right? So this is my clipping window, correct? Same thing, it is xw min, xw max. It is defined by yw min and yw max. This is the point in my window coordinate, right? So xw comma yw, right? So this has to be first converted to a normalized square, right? So we know that normalization square, it is a unit square, right? So with -1, +1, right? And -1 and +1. So first I'll be converting my xw comma yw to a point into a normalized square, right? Which we call it as x norm comma y norm, right? So again, this normalized point has to be further converted to our viewport coordinate, which is xv comma yv, right? For xv comma yv. So this particular point is in terms of viewport coordinate. This is the second type of transformation. First, we will convert the window coordinates to normalized coordinates. From there, once they are normalized, right? So with all the redundancy is gone, right? So that is why we go for normalization, so that the picture clarity, right? The clipped picture quality, clarity, its relative position, everything will be correct, right? So once everything is done, we will map it to the viewport coordinates, right? So what is the advantage of going for normalization? The clipping algorithms will be standardized, right? So in the next session, we'll be discussing about different types of clippings and what are the different types of clipping algorithms, right? What we have in our computer graphics, right? So in order to standardize those clipping algorithms, we go for mapping from window to normalized square, right? And from there we go for viewport coordinates, right? So in order to do that, what we are doing here is we have to consider the same equation, just we have to substitute, right? Xv min and yv min, right? So which is my leftmost point of my viewport coordinates as -1 and xv max and yv max as 1, right? So because I'm taking my point which is between -1 and +1, right? So you can see it is between -1 and +1. That is why my lowermost point, that is xv min and yv min, this is my point here, xv min and yv min, this will be -1, and this uppermost point which is xv max and yv max, this will be +1, right? So we have to substitute these values in our scaling matrices what we have defined earlier. Here we have to substitute, right? So if I substitute these values, I'll be getting one composite transformation matrix, which is a matrix for mapping from window to a normalized square, right? So you can see here we have written it as normalized square, right? But in the previous example, we wrote it as normalized viewport because directly we converted from window to viewport, whereas here we are first converting it to a normalized square, right? So how did we get these values? Just by substituting xv min and yv min as -1, right? So let us see one example, right? So in order to get this Sx value, what I do is I'll go to my Sx scaling factor Sx. What I have to substitute, xv min and yv min I have to substitute as -1 and xv max and yv max as +1, right? So +1 and -1, what I will get? 1 minus of -1. So 1 minus of -1 will be 1 plus 1, which will be 2. So 2 divided by xw max minus xw min, right? So that is what I have written here, 2 divided by xw max minus xw min, right? So the same way substitute for sy also. So if I substitute for sy, right, yv max is 1 minus yv min is minus 1. So 1 minus of minus 1, I will get it as 1 plus 1, which is nothing but 2. So 2 divided by yw max minus yw min. This is my sy. So 2 divided by yw max minus yw min. The same way substitute for your tx, right? So in my translation factor, right? So here also I have to substitute xv min as minus 1 and xv max as plus 1, right? So and I have to solve this, right? So if I solve this, I will get this particular value, right? So by just substituting the values, these values, right? So in the expressions for tx, ty, sx and sy, I will get my composite transformation matrix, which is used to map from window to a normalized square, right? So once I have mapped to normalized square, what I have to do? Again, I have to transform from the normalization square to viewport coordinates. That is the next method, right? So finally, we have to map it to viewport, right? So similarly, after the clipping algorithms have been applied, the normalized square, right? So with edge length equal to 2, right? So because here we got the normalized edge as 2, right? So with the edge length equal to 2 is to be transformed into a specified viewport, right? So this time what we have to do is we have to substitute minus 1 for xw min, yw min and plus 1 for xw max and yw max in the same scaling factors and translation factors, right? So let us see here, xw min and yw min I have to put minus 1, right? So what I do is I'll go back to my scaling factors here, xw min and yw min I have to substitute as minus 1, xw max and yw max I have to substitute as plus 1, right? So here upper value will not change, it will be xv max minus xv min. So here it will be 1 minus of minus 1, right? So 1 minus of minus 1 I will get it as 2, right? So scaling factor sx I will get it as xv max minus xv min divided by 1 plus 1, which is 2, right? So if I come here, you can see xv max minus xv min divided by 2, right? So how did I get this? By just substituting the value of minus 1 and plus 1 for minus 1 for xw min and yw min and plus 1 for xw max and yw max in our translation and scaling factors, we will get this equation, right? So this equation is called as the composite transformation matrix for converting from normalized square to viewport coordinates, right? So this is a simple example as to how we are showing a clipped triangle, right? So this is a red triangle, right? So which is clipped, that is what that is the example what is given in your textbook, right? So this is my video screen, that is my output screen. It can be a TV screen, it can be a monitor screen, anything, right? So this is my display window, right? So on this display window, inside this I have my viewport, right? So the object, right, the triangle which is from window coordinate, that it is mapped to the viewport coordinates, right? So that particular part of the object is clipped and it is displayed on the viewport, right? So like this we can do two types of transformation in order to convert from window coordinates to viewport coordinates. Directly we can convert window to viewport, or I can convert from window to a normalized square, again from normalized square to viewport, right? So clipping window to normalized viewport, what did we do? We have to clipping routines can be applied, right? Different algorithms can be applied using either clipping window boundaries or the viewport boundaries, right? So window boundaries means first we were setting xw min, yw min as minus 1, xw max, yw max as 1, right? Viewport boundaries means xv min, yv min we made it as minus 1, again xv max and yv max we made it as plus 1. That is what it means, right? So I am applying different types of clippings by applying the clipping window boundaries. Then I will get the normalized coordinates, they have to be transformed to the device coordinates, right? So finally we conclude that the unit square, it can be mapped to the output device by you making use of translation and scaling, right? So actually the transformation is nothing but we are scaling from window to viewport, and we are also translating that particular point from the window coordinates to viewport coordinates, right? So far we have discussed about what do we mean by clipping and what are the two types of transformations we have. The first transformation is mapping window to normalized viewport, right? Then the second one is mapping window to a normalized square. right? So normalized square again from square to viewport. Thank you.